So welcome to part 2 of lecture 8 of Math 2R03. In the last section or part, I talked about what the dimension of a vector space is. What we're going to do in this part is we're going to link dimension, span, and linear independence. And the following two theorems are going to show that if you know the dimension and the span, you can say something about linear independence. Or if you know something about dimension and linear independence, you can say something about spanning. So in particular, this all gets tied to the notion of a basis. So here's our first theorem that we'll prove. Suppose that you know that the dimension is n, and let's say you have n linearly independent vectors inside of V. Then what you get for free is that V1 through Vn is also a basis for V. So the way you should think about it is this theorem is telling you if you know the size of the vector space and you know that it's linear independent, you get for free that these set of vectors should also span all of V. And you also get that it becomes then a basis for the vector space. So let me show you how the proof of this works. Okay, so what we need to do, so we need to show that V is also equal to the span of V1 up to Vn, because we already know that V1 through Vn are linearly independent. Well, we can extend V1 Vn U1 up to Ut to a basis of V, because we know V1 through Vn are linearly independent, and our work from last lecture says you can always extend a set of linear independent elements to a basis. Okay? Now, since all bases of V have the same length, right, and because dimension of V is equal to n, we have to have that the number of elements in this list has to be n because it's a basis. Okay, so we have that n is equal to n plus t. But this only happens if t is equal to 0. So that means that we didn't add any new vectors to make a basis. So V1 through Vn is a spanning set, i.e. it is a basis. Okay, so we get a nice short proof of that result. The second theorem that we want to prove in this part is kind of a complementary result. And it says that, well, let's say instead of we still assume that we know that the dimension is n, but now let's say we know that V1 through Vn is a spanning set. Then we get the same conclusion that V1 through Vn is a basis. So knowing that the size and you have a spanning set, you get for free that those things, these vectors are also going to be linearly independent, provided you have the correct length of vectors. And how does the proof work? Well, since V1 through Vn spans our vector space, some subset of V1 through Vn is a basis of V. This is what we proved in last lecture. You can always take any spanning set and reduce it to a basis. Okay. Well, what we know is since the dimension of V is n, a basis must have n elements. Okay, so let's put these two ideas together. And so what we have is, so a subset of size n of V1 through Vn is a basis of V. But this, you're starting with n elements and you need a subset of size n, and there is only one subset. But the only subset of size n is the whole set that you started with, V1 through Vn. If you took any proper subset, you would have less than n elements. So these two theorems are great because they're kind of tying dimension and spanning sets and linearly independent sets. They're tying them all together when you're talking about a basis. So to check whether something is a basis, you either have to check that your n vectors are both spanned and are linearly independent, or you can talk about if you know the dimension and if you have the correct number of vectors, either spanning or being linear independent, you get that it's a basis of your vector space as well. So let me just give you kind of a quick example of how you could use this. Here are two vectors inside of F2, okay? And we know that the dimension of F2 is 2, that's what we talked about before, and 1, 2, and 2, 3 are linearly independent. And that's straightforward to see because this vector is not a multiple of the first vector. So I know without any further work that thus 1, 2, 2, 3 is a basis for F2 by applying one of the previous results. Okay. Now, before we move on, I just want to kind of give you a kind of a cautionary tale, maybe that's the best way of describing it, about how the dimension will depend upon your field F. Now this doesn't come up a lot, but you should realize that the dimension somehow depends upon F. And a good example to see here is when we look at the complex numbers, C1. Right, so we're looking at all the elements that look like A plus BI, where A and B are real numbers. Now this is a vector space over C and R, but the difference between them is that scalar multiplication works different, right? So as a vector space over C, you have to multiply by constants coming from the complex numbers. So scalar multiplication looks like A plus BI times C plus DI, and it gets sent to AC minus BD plus BC plus ADI. On the other hand, if we think of C as a vector space over R, the scalar multiplication differs by the fact that we can't multiply by any arbitrary complex number. We have to multiply by an arbitrary real number, right? So we have T, here's our real number, and then we're multiplying by an element in our set of complex numbers, and it gets sent to CT plus DTI. Okay, so there, C is a vector space over C and R. And the interesting thing now is over C, what does C1 looks like? Well, C is the span of the single element 1. Okay, so that's right. So right, because this looks like C times 1, where C is a complex number. But over R, it's a spanning set of 1 and I, right? Because you could think of every number as C times 1 plus D times I, where C and D are real numbers. And here I'm using the subscript to keep track of the coefficients. Okay, and over C, right, this is a basis. 1 is a basis over C for the complex numbers. But over R, 1 and I is a basis for C1, okay, where you're only allowed to use coefficients over R. So the dimension of over R using scalars, okay, we're keeping track of our scalars, of C1 is 2, but the dimension over C of the complex numbers is 1. Okay, so again, we're keeping track of the coefficients to keep track of coefficients. So just as a final statement here is whenever you have a field and you're thinking about the dimension of F over that field, it's always going to be 1, since the field F is always can be thought of as the span over where the coefficients are coming from F of the element 1. Okay, so this is something you just kind of pay attention to. Okay, that sometimes you have to pay attention to where your coefficients are coming from. And normally it will be very clear, and we'll try to avoid examples like this. But just so you know that if you're thinking of C as a complex numbers over the reals, it's a two-dimensional vector space. But if you're thinking of C1 as a vector space over 3, it's a one-dimensional vector space. Okay, so we'll pause there, and then we'll talk a little bit more about dimension in the next lecture, part.